Hello. Today what I want to talk to you today about is two concepts. I want to talk to you about a bilinear map and an inner product. And I want to talk to you about the relationship between the two. Sorry, not a bilinear map, a bilinear form. And let's talk about the inner product first. The inner product, there's four properties. So the inner product is a bilinear map, and it maps two vector fields to this vector spaces to the field of real numbers k, and it's something like properties are, the first one is, we use this notation, the angle bracket notation, u plus w v, here's argument 1, argument 2, equals u v plus w v. So it's the additive property in the first argument, and we also display the additive property in the second argument, v plus w equals u v plus w v, something like that. So that's additivity in the first and second arguments. The other property we have here, that's just another one, first property. The other property we have is symmetry in the second, or the symmetric properties, so we can write u, v, this equals, if we flip the arguments around, it's the same value. So that's symmetry in or just the symmetric property. The third argument we have is what we can call, I think they call it first degree homogeneity in the first argument. So we can write, if we have some scalar a multiplied u and v, we can bring this out to the front here, and we have a uv. The final property we have is, it's really maybe final two properties, and I'll show you what I mean, is this positive definiteness property, and we say that u v, the inner product thereof, is greater than or equal to 0. And this is the sort of the additional element of this is that the thing that's in addition to this is that we can say that if we have the identical vector, if we pass in the same vector for the first and second argument, this is equal to 0. If this statement is true, then it follows, IFF, that u equals the 0 element. So these are the four properties of the inner product. Let's talk about bilinear forms now. Bilinear form is a bilinear map. And it maps two vector spaces to the real field K. And what can we say? We use the notation in FEM. I see the notation in Gorbachev's book, not Gorbachev, whatever his name was, the 2009 book, the red one, second edition on PDEs. A of uv, I see this notation here, where U and V are elements of some field, some vector space. I keep on saying field. I really need to stop that. But the other notation is just some sort of B, U, V for bilinear. I like this one better. So the properties of the bilinear form are that it's bilinear, so it's linear in the first and second arguments, or actually not quite linear in the first and second arguments. Let me show you what I mean. B of U, U plus W V, that equals B of U V plus B of W V. And we have, this is the additivity, and we have additivity in the second argument. Additivity in the second argument. And we also have first degree homogeneity in the first argument, so we can say, or in both arguments, sorry, B of lambda, where lambda is some scalar. And it's also first degree homogeneous in the second argument. First degree homogeneity. So it's linear. Now if we restrict, actually before we restrict, let's define. If we define the Dirichlet second degree continuous vector space such that, denote with this D here, such that we have C, we have, maybe you can call it f of x, which is an element of C2, but at the in conditions, sorry, this should be defined between the range 0, L inclusive, such that f of x equals, sorry, f of 0 equals f of L equals 0. So all that means is we have second order, it's continuous in the second derivative, yet is 0 at the boundaries. So if we were to mark out f double prime with respect to x, we have something like this. So it goes. Okay, now then, if this is a function space, so if we were to do this for the elements of a bilinear form, then what? So if U is an element of this vector space, then we take the inner product, UU, that equals 0 to L of U of x squared dx. This is squaring something from C to D, so therefore that's always going to be greater than or equal to 0. And now notice that our fourth property of the inner product, that is, the inner product is always greater than or equal to 0, is also manifest in the bilinear form by restricting its domain to C to D. Or really, you could get it from any sort of restriction, that so long as this property is true. So in that way, the bilinear form used in FEM is an inner product. So thanks, and we'll see you next video.